Hello students. Today we are going to study a very interesting chapter called a square and a cube. Let us first begin with square numbers. A square number is the product of a number multiplied by itself. We write it as n superscript 2, read as n squared. For example, 1 times 1 equals 1, 2 times 2 equals 4, 3 times 3 equals 9. And 4 times 4 equals 16. But wait, we can even square fractions and decimals. Like this, 3/5 squared equals 9 over 25. And 2.5 squared equals 6.25. So you see, any number, whether it's whole, or a fraction, or even a decimal, can have a square. Now here's the special part. When the square comes from a whole number, we call it a perfect square. Examples: 1, 4, 9, 16, 25, and so on. These perfect squares are special because they follow neat patterns. Let's look at them. Patterns and properties of perfect squares. First, let's look at the units digit rule. Squares can only end in 0, 1, 4, 5, 6, or 9. They never ever end in 2, 3, 7, or 8. For example, take the number 43. It ends in 3, so it cannot be a square. Now, special endings. If a number ends in 1 or 9, its square will also end in 1. If a number ends in 4 or 6, its square will end in 6. Next comes the zeros rule. If a number has zeros at the end, its square will have double the zeros. For example, 10 squared equals 100. 100 squared equals 10,000. And here's the even-odd rule. If the number is even, its square is also even. If the number is odd, its square is odd too. These simple patterns make it much easier to check and identify squares. But there's more. A strong link between perfect squares and odd numbers. Let's explore. Here's an interesting observation. The difference between consecutive squares is always an odd number. 4 minus 1 equals 3. 9 minus 4 equals 5. 16 minus 9 equals 7. 25 minus 16 equals 9. So you see, consecutive squares differ by consecutive odd numbers. Now, another property. Every perfect square can also be written as the sum of the first few odd numbers. 1 equals 1, 4 equals 1 plus 3, 9 equals 1 plus 3 plus 5, 16 equals 1 plus 3 plus 5 plus 7. In general, the sum of the first n odd numbers equals n squared. And here's a neat checking rule. If you keep subtracting consecutive odd numbers from a given number, and the result becomes 0, then the number is a perfect square. For example, 25, subtracting odd numbers step by step, finally gives 0, so 25 is a square. But 38, subtracting odd numbers never gives 0, so 38 is not a square. Now, let's connect perfect squares with another fascinating sequence: triangular numbers. Triangular numbers are numbers formed by arranging dots in a triangle, like 1, 3, 6, 10, 15. Here's a special property. If we add to consecutive triangular numbers, we always get a square number. 1 plus 3 equals 4, and that's 2 squared. 3 plus 6 equals 9, and that's 3 squared. 6 plus 10 equals 16, and that's 4 squared. This shows us something amazing. Triangular numbers and square numbers are deeply connected. And once we understand squares, it's time to look at their opposite, the square root. The square root of a number is the value which, when squared, gives back the original number. For example, the square root of 49 is 7, because 7 times 7 equals 49. Here's something to note. Every square has two roots, positive and negative. But in class 8, we only take the positive one. Now, how do we check square roots? One way is by subtracting odd numbers, step by step, until we reach 0. Another way is by prime factorization and pairing factors together. And yet another way is estimation, comparing between two nearby squares. Now that we know about square numbers and their roots, let's step ahead into the world of cubes. A cube number, or perfect cube, is the product of a number multiplied by itself 3 times. For example, 1 cubed equals 1, 2 cubed equals 8, 3 cubed equals 27, 4 cubed equals 64, 5 cubed equals 125. So numbers like 1, 8, 27, 64, 125, and so on are perfect cubes. And now, let's look at a very famous number connected with cubes, the taxicab number. A taxicab number is a number that can be written as the sum of two cubes in two different ways. For example, 1729 equals 1 cubed plus 12 cubed, and also equals 9 cubed plus 10 cubed. This special number is famous as the Hardy-Ramanujan number. Perfect cubes also have a link with odd numbers. Here's the property. Every cube can be written as the sum of consecutive odd numbers. For example, 1 equals 1 cubed, 3 plus 5 equals 8, and that's 2 cubed. 7 plus 9 plus 11 equals 27, that's 3 cubed. 13 plus 15 plus 17 plus 19 equals 64, that's 4 cubed. So in general, for n cubed, we add n consecutive odd numbers. And just like we studied square roots, now we'll explore cube roots. The cube root of a number is the value which, when cubed, gives the original number. For example, the cube root of 8 is 2, the cube root of 27 is 3, and the cube root of 1000 is 10. Now, how do we check if a number is a cube? We use prime factorization. If the prime factors can be grouped into triplets, then it's a cube. For example, 3375. Its factors form triplets of 3s and 5s, so the cube root is 15. But 500. Its factors cannot be grouped into triplets, so it is not a cube. Successive differences. We noticed that squares differ by odd numbers, and cubes can also be expressed as sums of odd numbers. These patterns help us quickly identify perfect squares and perfect cubes. Finally, let's take a quick look at history. The Babylonians, around 1700 BCE, had lists of squares and cubes written on clay tablets. In India, Sanskrit texts used special words: Varga for square and square root, Ghana for cube and cube root. Great mathematicians also gave clear rules. Aryabhata, in the year 499 CE, explained squares and their roots, and Brahmagupta, in 628 CE, said beautifully, "The root of a square is that which, when squared, gives the square." We hope that you have understood the topic. You can now study chapter notes, watch video lectures and solve MCQ tests of this chapter on EduRev to ensure you score well in your school exams. And that's not all. You also get amazing courses for maths, science, English, Hindi, and much more for Class 8. Thank you.